So now I want to talk about optimality condition for convex functions, but this time we have constraints, and our constraints are a convex set. So subject to a convex set. But before going there, I want to talk about this concept of tangent cone. Many different people, many mathematicians, they define different concepts for tangent cones. For example, some people say that, the most general definition that I use here is this. So this is the tangent cone. The tangent cone to x, to set x, is all the points. So this is the tangent cone. Is all the points, is the closure of the cone formed by all half lines. Or say, for example, tangent cone is all of these rays that are emanating from x and emanating from x and intersecting x in at least one point y distinct from x, not this one. So any point like y. This is the definition of tangent cone. For example, tangent cone is here. But we have normal cone as well. So the normal cone is orthogonal to everything in tangent cone. So at least has a 90 degree from the tangent cone. So this is the normal cone. All of these points are normal cone at this point. That's why we say n for set x at x. So here x and x is this. Set x is here. So normal cone is red. The normal cone, all of these directions that go out. For example, here it could be all of these points that are going out are normal cones, are inside the normal cone. And so, as usual, when you want to say that some point x hat is optimal, you say it depends on the situation. For example, if for example, let's say this one. If x is here, if x1 is here, then no problem. You just say that 0 should be inside the subdifferential at point 1. x1 is here. But if x is here, x2, but if x is here, then you can say that you are interested in points that are this is the normal cone, and this vector is minus gradient of f at point x2. So it should satisfy, zero should be inside the subdifferential at point x hat plus a normal cone at point x hat. And this is, you can say that this holds because we want the direction of f to be inside this one. We want to be inside the normal cone. So if just rewrite this, you will see this. So it's a very natural thing. And I want to show you the concept of projection. For example, we want to minimize some function, but this time, let's say your function is, you want to minimize x minus 1, the distance, the Euclidean distance between x and y. And so subject to this one, subject to x is in a convex set. So x hat is an optimal solution, as we said before, if 0 is inside subdifferential at point x hat plus normal cone of set X at point X hat. And so the geometric intuition behind that is something like this. You have a point Y. You want to minimize distance between this set X and Y, but you want to minimize distance, and this is a convex area. This is the convex zone. So X could be anything, so this is the minimal solution. This is the optimal solution, X hat. So X hat satisfies is an optimal solution, and so this one holds. And just work on this, because now f is a differentiable function, so no problem. 0 is inside. The differential of that is x hat minus y. Now you see why I use 1 over 2. So this one plus normal cone for set x at point x hat. So we conclude that y minus x hat is inside the normal cone at point x hat. And this is exactly when y minus x hat, the inner product between y minus x hat and x minus x hat for any x inside your set, for example this one, the inner product, let's say the inner product between this vector and this vector, because because the angle is greater than 90 degree, so the inner product is less than 0. And this is an important property that holds just for convex sets. And let's say, so let's talk about separating hyperplane. It's an important theorem in Hilbert space, and here it's much simpler because we are in Rn. And so if you have a convex set X, then it says that you will find a hyperplane such that y, you can separate by y and the set X by a hyperplane. So we have separated by this hyperplane H. So your hyperplane H can be defined as all points S transpose X is equal to B. So H plus and H minus, it's different size of the hyperplane, and it can be shown that S is Y minus X hat. So X hat is projection. So its hat is a projection of Y. So if it comes here, this is X hat. This is the projection of Y onto X hat. This is X onto X. So this is the important theorem separating hyperplane in functional analysis. And here it's so easy because we are just dealing with Rn. And the next thing I want to talk is projection onto a convex set is a contraction. It's so important, I want to write it. Projection onto a convex set is a contraction. So this operator is just try to reduce the distance. So I want to prove that y1 minus y2, the L2 norm, is greater than or equal to x1 minus x2. So if we have a convex set like X, and we have 2 points x1 and x2, so y is the y1, project y1 onto x is x1, and projection of y2 onto x is x2, I want to say that the distance between y1 and y2 is greater than distance between x1 and x2. So we know from the my previous talk that y1 minus x1, the inner product between x2 minus x1 and y1 minus x1 is less than equal to 0. And on the other hand, so both of them holds. On the other hand, y2 minus x2 and x1 minus x2, the inner product is less than 0. So let's work on this. We conclude that y1 minus x1 and the inner product between this and x2 minus x1, we just simplify that. x2 minus x1 is less than 0, and y1 minus y2 minus x1 minus x2 and x2 minus x1 is less than 0. So we can write that y1 minus y2 minus x1 minus x2, and the inner product between this one and this one is greater than equal to 0. One more time, we can write y1 minus y2, we are just separating them, x1 minus x2 minus x1 minus x2, and x1 minus x2 is greater than 0. And now I want to use the Cauchy-Schwarz. Remember the Cauchy-Schwarz inequality, that if you have two vectors u and v, the inner product between them is less than equal to norm of them, the multiplication of norm of them. So here I can use this. So u and v, u is this one and v is this one. So we have an inner product. So the multiplication of norm of them, it means y1 minus y2, the norm, multiplied by x1 minus x2 is greater than y1 minus y2 and x1 minus x2. And the rest of them are the same. You just simplify this as well and just write this is the norm of x1 minus x2 2. And then we are finished. We are almost finished. And now we can say that y1 minus y2 is, the L2 norm is greater than x1 minus x2. So in other words, this projection operator is so interesting because it tells you that this projection operator, it is going to reduce the distance between your points. And it plays an important role in modern optimization. All problems are all ideas, proximal gradient descent, bundle methods, mirrors, all of them are using some properties of convex functions and convex sets. So you see why this is the case, and I will tell you in future that proximal operator is just generalization of projection. So projection operator is just a special case of proximal operator, and that is very interesting in optimization of functions that are non-smooth. And for example, lasso is non-smooth objective function, and so of course in multi-objective optimization you will have some problems with non-smoothness as well. In recent work of Robert Tipshirani, LessoNet, he uses the idea of you want to shrink, you want to do feature selection, use the sparsity and combine it with the neural network, which is a feed-forward neural network. Simultaneously, you want to do a sparse selection, and so that other the interaction terms is important as well, because the lasso cannot model the interactions, it just has the main effects. But in the LessoNet, which is the latest work of Robert Tipshirani, you have a problem of non-smoothness. That's why you need to learn about all proximal gradient descent. Of course, he used the proximal gradient hierarchy, proximal gradient method to solve the optimization problem. So his objective function has become a non-smooth objective function. So he needs to work on that. And he has shown that his results are much better than even HSIC and other popular methods in machine learning, which is so interesting